Hello, so in this video I'm going to be explaining an explicit differentiating scheme in which we relate temperature to position and time, in which these are metal bars that are being heated up. So I went ahead and divided, these are three separate metal bars, and I divide them into sections. So we could say this is metal bar initially at time is 0. I need to change the t though. So for future reference, capital T will be in relation to temperature, and a lowercase t will be in relation to time. And I'll have T1 equal delta T, and T2 equal to delta T. So you might ask, well, where do we go from here? Well, the equation we need with heat generation, so keep in mind this is with heat generation. We have a different equation for without that I will also show in this video, and it's similar to one of my previous videos. So we will have the second partial derivative of temperature related to position. So again, capital T is temperature and X is position. And we will have that plus Q dot over T, but this is lowercase t, so it's time. And we're going to have that equal 1 over alpha times, as a horrible dot, the partial derivative of temperature in relation to time. And this is the equation that we would need with heat generation. Now, without heat generation, I'll go ahead and erase this because I'm going to need a decent amount of room for this. So, without heat generation, we are going to have the partial derivative of temperature in relation to time. This first part may seem familiar now. We're going to have alpha, which is thermal diffusivity. I don't think I said that earlier. I should have clarified. Alpha is thermal diffusivity. And we are going to have that to the second partial derivative of temperature in relation to position. So from this, we can further get partial derivative in relation to x being multiplied by the partial derivative of temperature in relation to x. And that is this portion right here kind of being expanded. As you can tell, we have the two partial derivatives of x in the denominator, and we have t right here. So I will erase this now. Well, the notation we are going to use when writing these equations is we will have temperature at some position j So J relates to the position, and at some time N. So if I were to say just as it is, J and N at position J and position N, that means the current position at the current time. If I were to say N plus 1, that would mean the next incoming temperature at that time at the same position. If I were to say J plus 1, then that would mean the next position at the same time. So, with that out of the way, we can go ahead and start creating some equations. And all of these equations are going to use the form I just explained. So it's crucial to understand that part before continuing on. So we are going to have the temperature at the current position, but the next upcoming time, we're going to have that minus our current temperature at the current position and current time. And we are going to have that over, that was a horrible line, over the change in time. So this is the left side of the equation. We are going to have it equal to what is coming up next, which was the right side of the previous equation. So we are going to have alpha. This will be multiplied by, I'm worried about running out of room up here and it looking confusing. So I'm going to lower the alpha. So we are going to have that multiplied by T to the J plus 1 N, which is the temperature at the current time of the next position. And we're going to have that minus the current temperature of the current position, current time. We are going to have that over delta X, because if you remember from the previous equation, we had it over delta X. So then the next portion, I hope I do not run out of room, but we are going to have the temperature at the current position and time, and we are going to have that minus Tj minus 1 over n, also over delta X. So essentially what this is saying, temperature at the current position and current time minus the temperature at the current time but of the previous position. So you may think this is all we need to do, but we actually need to divide this all by delta X. Because if you remember in the denominator, we had what was essentially the partial derivative of x squared, which we need to do this to make sure this is change in x squared. So now with some algebra, we can simplify these. So I will erase these because I'm running out of room again. So we want to have the temperature at the current position, but the next upcoming time by itself on the left side. So essentially, it'll be easier to see one side, write it all out, but we moved everything but this to the other side and simplify the other side. So we will have t at the current position and current time on this side, because originally it's being subtracted on this side, so we just moved it over. And we will have plus, oh my, that is a horrible alpha. We will have plus alpha, and if you remember, alpha was being multiplied by this massive amount of fractions and stuff, but those fractions simplified will simply be t j plus 1 and minus 2 tjn plus tj minus 1 and all over delta x squared. And we also, because on this side, if you remember, we had tjn plus 1 minus tjn over delta x. Well, we can't forget about us multiplying by the delta x, so this will also be multiplied by delta x. Not delta x. No, that was delta t. Yeah, it was over delta t. I was about to say all the delta x's should be on this side. So now we can, oh my, that I wrote that very tilted, but we can simplify this even more. So I will write out the simplified version. Essentially, what we are doing is just removing the delta x squared out. So we will have t to jn plus, we will have alpha delta t over delta x squared times t j plus 1 n minus 2t jn plus t and j minus 1. So this equation right here is the ultimate answer to deriving our forward differentiating scheme. And just to go over one last time, we have the temperature at the current position of the next upcoming time equal to the temperature at the current position current time plus alpha delta t divided by delta x squared. And we have the temperature of the next position at the current time minus temperature of the current position current time multiplied by 2 as well, plus the temperature at the previous position but current time. So that is the derivation of the forward differentiating scheme.